All right. Greetings. I'm going to go ahead and put my mug up here real quick. I know that's always fun. Anyway, like my new sweatshirt. I love my new sweatshirt. Anyway, I had one. I had like this golf type fleece thing that was really good, but stupidly I left it in a lecture hall. Went back a couple for the next lecture. Oh, gone. Anyway, so what we're going to be doing in this lecture 3 here, is one of the more. It seems like it's difficult for a lot of students, and I wanted to show you a few changes that I've made to your Blackboard site. One is I am so used to teaching off of the slides from Cutnell and Johnson, the publisher that charged you money, so I'm stealing their slides. I mean, I've got them. I figure I threw business their way for 4 years, so we made enough. They can give me some slides anyway. And as long as I say that they're from Cutnell and Johnson, I don't think they'll come after me for copyright or anything. They might say, well, that's kind of cheesy. You're not using our product, but you're using our slides. Well, you're a publisher. You're cheesy. Anyway, I'm kidding. People got to make money. So and it's a legit business. So anyway, we're doing we're doing projectile motion, and what we're going to be doing is we're going to be throwing balls, hitting golf balls, hitting baseballs, and we're going to be doing it with where we discount atmosphere, which is absolutely ridiculous. Because I mean, if you're going to really calculate these things, and one thing that's upsetting me a little bit is that ESPN has taken down their home run tracker. They had this great home run tracker little spreadsheet that you could open, that I had on speed dial, and you could go look at like a Judge home run or an Eric Hosmer home run, and go and see that the schoolhouse answer would have that ball going like 680 feet. At the furthest that any human being with a wooden bat could hit a baseball, a major league baseball, even if you did it at Coors Field, which is where the Rockies play, way up high at 5,000 feet. I mean, you could go bat in Nepal if you wanted to on a dry day in Nepal, and we're at 10,000 feet, and still not hit a baseball that far. The maximum distance a baseball can actually go is about 500 feet, which is ballpark 170 meters, 160 meters, something like that. So, these answers that we might come up with are a little bit silly. And we'll also talk about the maximum angle. The best angle that you should do it is not the schoolhouse answer that we're going to do here. So anyway, just wanted to clarify a few things like that for this. This is your lecture 3, and this will cover projectile motion, and I'll probably actually throw in the related rates, which I like to just keep it nice and simple, nice and straightforward. I'm not going to make you do, crossing a stream and what angle you're going to have to do to get to the other side straight across. I just want you to know that how in one dimension how two things are related to each other. And then that will help us next year when we look at special relativity and going the speed of light and stuff like that. All right, so out here for right now, that was just your intro. I wanted to show you the board here, and I've added these PowerPoint slides. These are the Cutnell slides, and these are the ones I'm going to be working off of. I've also added this policy for making up a missed lab. So if you're going to miss lab, like some of you have already experienced the flu epidemic, and so there's the policy. You don't email me. Don't email me if you're sick. I don't care. No, actually, I do care. I mean, I do. I care about you. But as far as taking care of business, we've got it set up so that you can. All right. All right. So, because I thought, after a few attempts, I thought the chapter slides that you get what you pay for from this textbook publisher were not what I needed. Okay? And, they make no bones about it. That's not what they're about. They're about providing you the information. Now, the information is the same. So you're going to get our slides, and you're going to get a little bit different perspective from the textbook that's free that you download. All right. So let's look at the PowerPoint slides here. And let's go to chapter 3, which is good old two-dimensional motion. Now, ignore this, except that this is kind of cool. I was going, why are you being such a jerk? Anyway, there we go. So let's set up the slideshow. And I understand that I have to record this now in 1080 or else you can't see it. So there we go. Look what happens. These are vectors, all right. And so when you're going around your initial position and initial displacement, this is the it's a bunch of radial calculus is actually what we do. V is the average velocity. However, when you're going around a track and the limit as t goes to 0 of it gives you your instantaneous velocity, we've already looked at that. I don't know why we're looking at these. Definition of average acceleration. Equations of kinematics, we've already done. This is what we've already done. All right, now, here's something going in the x direction, okay? Here it's taking off in the y direction, okay? So you've got an acceleration going up here, and so the overall movement of this thing is this. It's a parabola with Vx and Vy coordinate, with x and y coordinates, all right? And that's why we spent all that time doing the, kind of working on the vectors, Vx and Vy, all right? So if we do this problem, all right, so here we go. In the x direction, the spacecraft has an initial velocity component of 22 meters per second, okay? And an acceleration of 24 meters per second squared. Whoa, that's really accelerating fast, all right? In the y direction, and now it's got an initial velocity of 14 meters per second and an acceleration of 12 meters. Whoa, at a time 7, find x and vx, find y and vy, and then find the final velocity of the aircraft. So let's do that real fast, and then we'll move on. Okay, then we'll move on. All right, so let's do that one real fast. Let me hit escape. And let's go to, oh, I haven't turned on my ladybug yet, but it's turned on now. 22, 24, 14, and 12, right? So this is lecture 3, and we're going to call it 2D motion. All right, this is lecture 3 in two-dimensional motion. I need to expand this, and I probably need to go ahead and do this a little bit. There we go. That'll be nicer. That's better. All right, so we have XY coordinates here. Had that aircraft. Okay, there's my little aircraft. One didn't look like this. Had an initial velocity in the x direction of 22 and 24. Okay. 22 meters per second. Acceleration in the x direction, 24 meters per second squared. So it's going 22 meters per second now. Little quiz. When t equals 1 second later, how fast is it going to be going in the x direction? If it's accelerated, this means we're adding 24 meters per second every second. So it'll be going 46 meters per second. I'll always throw a little quiz at you like that. And in the y direction, was that 14 and 12? V naught y, and I want you to get used to this. X direction, y direction. V naught y is equal to 14 meters per second, positive, and it's also accelerating. Y is 12 meters per second squared. All right, so what I'm teaching you to do here is we'll do all the work in this side, do all the work in this side, and at the end we combine them. All right? So here we go. So, and t equals 7 seconds. So x, the distance in the x direction that it went. So what's going to happen is it's going to go a distance in the x direction. At the same time, it's going to go a distance in the y direction. And so it looks like this. And it's going to meet up here somewhere. T is equal to 7 seconds. That's for both of them. It's not in a different dimension on each one. All right. So its position after 7 seconds is equal to v naught x times t plus 1/2 at squared, axt squared in the x direction. And that will be pretty big. That's its x position. So we're going to take 22 times 7 plus 0.5 times 24, woo, times 7 squared. That's 742 meters. And its final velocity in the x direction is equal to v naught in the x direction plus the acceleration times the time, which will give us 22 plus 24 times 7. And this was, I'm sorry, this was 22 times 7 plus 1/2 times 24 times 7 squared. All right, and that's where it goes. So 22 plus 24 times 7 gives me 190 meters per second in the x direction. Let's do the same thing in the y direction. Y direction, same formula, but this time we're using the y components, these guys. V naught y times t plus 1/2 at squared. That gives me the y, and then the v final in the y direction is v naught y plus acceleration in the y direction times time. That one comes out to be 14 times 7 plus 0.5 times 12 times 49 again, 7 squared. Whoops. $392 meters, and this comes out to be 14 times 7. Oh, not times 7. Not there. Just clear over there. This will be 14 plus 12 times 7, which will give us 98 meters per second in the y direction. And so at the very end, we really don't have the displacement, okay? I really can't say what's its displacement or what distance did it travel. I can't really say that, all right, because it went like this, and here it is. And so if I want to calculate this distance here, we're not going to do that. That's beyond the scope of this course. That's like chapter 5 in calculus. You do that problem, all right? We're not doing that, all right? But we can find at this point Vx was equal to 190 meters per second. And Vy was equal to 98 meters per second. And I can go, oh, V final y is equal to 98 meters per second. And I can say, well, the final velocity at this juncture then, here's the little trick I can do. I can take this V final x, this is why vectors are fantastic to work with. And I can just go, move this vector over here. Aha! Combine it like this. We did this in class. You know how to find V final now. It's going at 190 squared plus 98 squared. You all are even sharp enough you can figure out the angle that it's flying. So we can take 98 squared plus 190 squared. Now on my calculator, I can do this. I can go second square root. Whoops. I can go second square root 190 squared. It gets tricky. Plus 98 squared. Then take the square root. And I get 213, which makes sense to me. 213 meters per second. And the angle will be the inverse tangent of 98 over 190. .3 degrees. I don't know if they asked for that. Let's see what the slide says. Reasoning strategy, we already went through all that, filled in all those boxes. Is that what I got? Oh, I got 742. Okay. All right. I was like, uh-oh. And I did 392 and 98 meters per second. Okay, so we got all that. And there we go. They were doing 2 sig figs the whole time. That's fine. I was doing 3 sig figs. So there we go. There's the equation of kinematics of two directions. Now we're going to talk about projectile motion in the next slides. Okay? And projectile motion, we're just talking about under the influence of gravity alone. All right? Okay, so out here. So that's enough for right now.